Now we will discuss about shortest remaining time first algorithm. This is one more CPU scheduling algorithm and this is related to your SJF. Okay. So shortest remaining time first is also called as preemptive SJF algorithm. That is preemptive shortest job first algorithm. This shortest job first that we have discussed is actually non-preemptive. Okay, so here what we will do, we'll make this particular SJF to preemptive so that it will become shortest remaining time first. So here it is similar to your SJF, that is the criteria will be your minimum of burst times, but here it is minimum of lowest remaining burst. Okay, lowest remaining burst. So how it will be done? There are two cases. Let's see. A process P1 continues to execute until the next process arrive to ready queue. Okay. So if P2 arrives and P2, suppose that see here, P1 is having 5 milliseconds of burst time. Okay, then it will execute up to 2 seconds, so that the remaining time will become 3 milliseconds. But a new process P2 came at time t equal to 2. So at time t equal to 2. At time t equal to 2, a new process came, that is P2, with 1 millisecond of time. Then the remaining time of P1 equal to 3 and the burst time of new process equal to 1. Then what will happen? The previously the currently executed process P1 will be preempted and sent back to ready queue, and the new process P2 will be loaded into CPU. Okay, so that is what happens. Now let's take a problem, it will be clear. So now look at this particular snapshot where there are four processes P1, P2, P3, P4, and they are arrived at 0, 3, 5, 6, and the burst times are 7, 3, 5, 2. Now let's go to step 2, ready queue. Okay, so at time t equal to 0, there is only process that is coming is P1. There is no other process in the system. There is only one process came to ready queue, and that is at time t equal to 0. Okay, so this process, regardless of how much burst time it is having, we need to load it onto CPU because there is only one process. So t equal to 0, which process came to ready queue? P1. So P1 continues to execute until the new process arrives. When the new process arrives at time t equal to 3. So it will execute up to 3. Then at time t equal to 3, a new process is arrived. Now after arriving the new process, this process burst time equal to 3. Okay. Now how much time it is executed? 3 seconds. So the remaining burst time is 4. Now these two will be compared. Okay, these two will be the remaining burst time of currently executing process and the new process burst time is compared. Now which one is minimum? P2 is minimum. Now P1 is sent to ready queue and P2 will be loaded to CPU. Now look at here, P2 starts executing. Okay, now up to what time P2 will continue to execute? Up to a time t equal to 5, P2 will execute. Okay, t equal to 5, P2 will execute. But now look at here, a new process at time t equal to 5, P3 came with a burst time 5. Now what is the remaining time of P2? 1. Okay, now both are compared, P2 and P3 are compared. If I compare these two, which one is having lowest burst time? P2 only. Now P2 is continue to execute, its remaining time equal to 1, that is up to 6 it will execute. Now its execution is completed, P2 execution is completed. Now at time t equal to 6, P4 came to ready queue with burst time of 2. With burst time 2. Now look at here. At time t equal to 6, P1 has remaining burst time 4, P3 has burst time 5, P4 has burst time 2. Now which one will be scheduled out of these three? P4 will be scheduled. Now as all the processes are come to system, there is no new process is arriving here, so it will be P4 which will be executed up to 8 milliseconds. Then P4 execution is completed. Okay, then P1 and P3 having 4 and 5 as the burst term, so P1 will execute up to 12. Okay, then there is only one process left, that is P3 with burst time 5, so it will load P3 and execute up to 12 plus 5 17. Okay, so write down the completion times. P1 completion time 12, uh, P2 completion time 6, P3 completion time 17, P4 completion time 8. Okay, now write down the turnaround times. If you write the turnaround times, it will be 12 and 3, 12, 2, this one 5, CT minus turnaround time minus PT 5, 0 and 7, 0. So if you calculate it, you will get this will be 29 divided by 4, because we have 4 process, so it will be 7.25 and it is 12 by 4, so it is 3. Okay, average waiting time and average turnaround time 7.25 and 3. Okay, now as we have finished all the CPU scheduling algorithms, now let's see the some special cases of all these algorithms. See, okay, sorry, one more thing. SRTF is also not possible to implement because the criteria is burst times. The criteria is burst times, because CPU burst execution time, we don't know exactly how much time it will take to execute. But if you compare, why we are still using the same reason as SJF, we will take average waiting time and average turnaround time, and we'll compare it with practically possible algorithms, and which algorithm is nearest to this performance of SRTF, we'll consider that that particular algorithm is efficient. Now let's see here, FCFS is practically implemented, round robin is practically implemented, priority algorithms are practically implemented, and the algorithms SJF and SRTF are not practically implemented. Okay, so next. Now let's see some special cases in all scheduling algorithms. First one, we'll start with FCFS. FCFS, the criteria is arrival times. That means the process which comes first, that will be executed first. There is a problem called convoy effect. Okay, so what is convoy effect? When a, uh, a process P1 having high burst times, okay, but P2 having low burst times. Okay, see, I will tell you. So let's see here, the P1 is having the burst time of 24, P2 is having the burst time of 3, very less as compared to P1, P3 is having burst time of 3, which is compared to very less, which is compared to P1. Okay, now let's see here, P2 and P3 are very smaller processes as compared to P1, that is 24. Okay, now what will happen, because P1 arrived first, P1 is arrived first, and P2 P3 are arrived after P1. Now look at here, look at the problem here. First P1 will be executed, the Gantt chart. First P1 will be executed, it will be executed until 24 milliseconds, because it is non-preemptive. FCFS is non-preemptive, it has to execute and come out, then only P2 will be loaded. It will be loaded for 3 seconds and it will be loaded for 3 seconds. Okay, so what is convoy effect? When the higher burst time process is executing in the CPU, all the lower burst time process have to wait until the higher burst time process is executed. Okay, long burst time process is execution completed. Okay, its execution completed, lower burst time process has to wait. Okay, so that is called convoy effect. This is called convoy effect. The next one, the next case is starvation. Okay, the next case is starvation. Starvation will happen in SJF, SRTF, also in priority schedule. See, this SJF and SRTF are special case of priority schedule. Okay, so what is that? SJF and SRTF are special case of priority schedule. Okay, so they are special case of priority scheduling. How? Let's see. If P1, P2, P3, assume that P1 is executing with uh, burst time of 7. Okay, then after 2 seconds, P2 came with burst time of 4. Okay, then what is the remaining time? 5 and 4. So P1 will be preempted and P2 will be loaded into CP. Then before completion of this particular thing, that means at the time P2 is finished, there is one more process that is coming with the lowest burst time than P1. That is this one. That is at the time of P2 is finishing. Now P3 came with 3 and compares with P1 and P3, and P3 will be executed. Now before P3 completes execution, there is one more process came with 4 again. Then it will compare with P1 and P4. Now you compare with P1, P3, P4, it will be P4 before P1 is executing, P4 will execute. Then P5 will be there. Again it is coming with 3 milliseconds, and one more process P6 comes with 2 milliseconds, and it will continue to come. That is, even after P100 you cannot execute P1. That means you don't know when P1 will execute. Okay, when P1 will, you cannot determine the time that P1 will be executed. That means your process, you cannot decide when this particular process will be executed. That is when in SJF and SRTF, when a lower burst time process keep on comes to system, they keep on comes to system, then the higher burst time process, higher burst time process has to wait an indefinite amount of time. How much time? You don't know how much time you will, this particular process will be scheduled. So this is called starvation. This is called starvation. So it's a special case of priority scheduling. So the starvation will also come in priority. We can simply say that priority scheduling also, every process will be having some particular priority, will be assigned to some particular priority. So here also, if a process P1 has priority 2 and P2, while it is executing, P2 comes with priority 3, P3 comes, then P3 comes with priority 4, while it is executing, P4 come with priority 5. So all these higher priority processes, they are keep on coming to system. Then this particular process P1, we don't know when this particular P1 will be scheduled, and that this particular P1 will be scheduled. Okay, so that is how. And this particular P1 will be starved, and it will take a long time. That is, it may take hours or it may take uh, days to execute. Sometimes it will not, it is not possible to execute if we have this particular problem, starvation in priority. And I already told you, SJF and SRTF are special cases of priority scheduling where the criteria is burst times, minimum burst times.